Welcome back to the Deep Dive. This is where we dive into complex research and pull out the key knowledge tailored just for you. Today, we are tackling, well, arguably the biggest topic there is.
Yeah.
Our home, planet Earth.
Mm-hmm.
The whole 4.5 billion years story.
Mm-hmm.
And to kick things off, how about a slightly mind-bending bit of physics? You know, when you think highest mountain, everyone says Everest, right?
Right. Yeah, that's the common answer.
But if your goal was actually to get as far away from the center of the Earth as possible, you wouldn't climb Everest.
No, you wouldn't. You'd head to Ecuador.
Exactly. To the top of the Chimborazo volcano.
And that little factoid, it actually perfectly sets the stage for our deep dive today.
How so?
Because it's a direct result of Earth's shape, its geometry. You see, the planet spins really fast, constantly.
Okay.
And that rotation causes it to bulge out around the middle, around the equator. It's not a perfect sphere.
Right, like spinning a water balloon, kind of.
Sort of, yeah. And because Chimborazo is very close to the equator, its peak sits on top of that bulge.
So it gets that extra boost.
Yeah.
Distance-wise.
Precisely. It makes it the single point farthest from the planet's core. Just over 6,384 kilometers away from the absolute center.
That's incredible. It really shows the kind of forces shaping our world. And that's our mission today, right? So really unpack this planet's entire story. We're using our stack of materials like the Ultimate Owner's Manual, looking at everything from the deep internal engine, the magnetic field.
All the way out to the atmosphere, the oceans.
And crucially, the human impact. Where we fit into this whole picture and, well, the planet's future.
And what all the research really underscores is just how unique Earth is. I mean, obviously, it's the third planet from the sun.
Yep.
But it's also the largest of the 4 rocky terrestrial planets. And maybe most importantly, it's the densest.
Density. So that points to a heavy core. Lots of metal.
Exactly. A really significant iron-nickel core driving intense internal pressures and heat.
But the real headline, the thing that makes Earth truly special,
is life.
Yeah. It's the only place we know of anywhere in the universe that definitely harbors life.
And the fundamental reason for that, as far as we can tell, is liquid water. Lots of it.
We're essentially an ocean world.
That's a great way to put it. Almost 71% of the surface is covered by the global ocean. That vast amount of liquid water is, well, it's the foundation for pretty much everything else we'll discuss.
Okay, so let's ground this conversation with some basic stats. Just the vital signs, if you will.
Good idea. So the average radius is about 6,371 kilometers. Remember, that's an average because of the bulge.
Right.
The total surface area, it's huge, 510 million square kilometers.
And the split is about 71% water, 29% land.
Correct. 70.8% and 29.2% to be precise. And then there's temperature. Despite, deserts and ice caps, the global average surface temperature is remarkably stable.
What's the number?
It averages out to about 14.76 degrees Celsius, and that's 58.57 Fahrenheit.
And that temperature range is absolutely critical.
It's the sweet spot. It's what allows all that water to stay liquid on the surface, which, again, is key for life as we know it.
All right, before we dive into the billions of years of history, let's just think about the name itself. Earth. It seems so simple, so fundamental. Where does that word even come from?
It's a fascinating question, actually, and the answer is, well, it's very literal. The name is deeply connected to the ground, the soil.
Okay.
Our modern English word earth comes directly from an old English word,
Or.
Yeah, or. And it primarily meant, the ground you walk on, the soil you dig in, dry land as opposed to the sea.
So we literally named our planet dirt.
Pretty much. And if you trace it back even further, to Proto-Germanic, you find the root erush. And you see related words, cognates, in basically every Germanic language. They all circle around that same core idea.
Yeah.
The physical ground, the material world.
It's kind of powerful, isn't it?
Uh-huh.
Naming the whole world after the part we could touch and see long before we knew it was a sphere floating in space.
It really is. And that connection to the land naturally led to personification, thinking of the earth as a being.
Like Mother Earth.
Exactly. You see it in Roman mythology with Terra, or sometimes Tellus. She was the goddess of the earth, the land.
And the Greek equivalent was Gaia, right?
Right. Gaia, the primordial earth mother goddess. Very foundational figure.
So this idea of the earth as a maternal entity, it's ancient.
It seems to be almost universal. The sources we looked at even point to a parallel in late Norse mythology. There's a giantess named Jord.
Jord.
Yeah, Jord, with an umlaut over the O, often anglicized without it. She was identified as the personification of the earth and, interestingly, the mother of Thor.
Wow. Okay, so it's a recurring theme across cultures.
Definitely. Treating the land, the Earth, as a living, often maternal force.
So we've got Earth, Terra, Tellus, Gaia, Ura, which brings up a neat little linguistic point you sometimes see, the capitalization. Why is it sometimes lowercase Earth and sometimes uppercase Earth?
Ah, yes. Good question. It really comes down to context and grammatical precision. We use the capital E, Earth, when we're treating it as a proper noun. Specifically, the name of our planet, putting it in the same category as, say, Mars or Jupiter or Venus.
Like listing the planets in the solar system.
Exactly. It's a specific celestial body. But lowercase e, Earth, is still super common, especially when it's used more generally, often with the in front of it.
Like the atmosphere of the Earth.
Precisely. Or talking about gravity, pulling something towards the Earth, or in everyday phrases like,
What on Earth?
yeah, exactly. What on Earth? It's almost always lowercase there. It refers more to the ground, the world around us, rather than the specific astronomical object.
Makes sense. And those older names, Terra, Tellus, Gaia.
Do they still get used?
They do, yeah, in specific contexts. Terra is quite common in scientific writing, especially planetary science or geology. When comparing Earth's features to Mars, for instance, you might see Terra used generically for land. And it's a staple in science fiction, of course.
Like terraforming. Exactly. Tellus is rarer. It tends to be used more poetically or in literature when you really want to emphasize that personification of the planet.
And Gaia, that one seems to have taken on a new life recently.
It really has. Less for poetry, much more because of a major scientific concept.
The Gaia hypothesis.
That's the one.
Okay.
While Gaia itself is relatively rare in traditional English outside of mythology, it became widely known in the mid-20th century thanks to that hypothesis, which we'll probably touch on later. It views the Earth as a whole, interconnected, self-regulating system.
Interesting. And how do you say that one? G-A-Y or G-Y-E?
Good point. You hear both. Giye is very common now, but the pronunciation more rooted in the original ancient Greek is often cited as Gyiwe.
Huh.
The fact that our world has all these different names and ways of thinking about it, Earth, Terra, Gaia, really shows how central it is, to our science, our stories, our whole understanding of where we are. Okay, let's rewind the clock. Way back. 4.5 billion years, give or take. How did this all begin?
The Big Bang happened way before that, obviously. We're talking about the solar system's formation, right?
Right. The prevailing theory is the nebular hypothesis. Basically, a giant cloud of gas and dust left over from older stars started to collapse under its own gravity.
And most of that stuff formed the sun in the middle.
Exactly. But a disk of material was left spinning around it, and within that disk, things started clumping together. The absolute oldest bits of material we found in meteorites, the building blocks, date back to 4.5682 billion years ago. Let's call it 4.57 billion, or for giga annum.
Okay, 4.57 billion years ago for the starting materials. How long did it take for Earth itself to form from that dust cloud?
Well, the consensus seems to be remarkably quickly, actually, at least on a cosmic scale.
Okay.
We're looking at around 4.54 billion years ago for the main formation,
Right.
plus or minus maybe 40 million years.
So the actual process of accretion, where dust became pebbles, pebbles became boulders, boulders became planetesimals, and they all smashed together. That took how long?
Roughly 70 to 100 million years, which sounds like a long time to us, but in the lifespan of the solar system, it's pretty rapid assembly.
And almost immediately after Earth formed, something incredibly dramatic happened.
Oh, yeah. Arguably the single most significant event in Earth's early history, the formation of our moon.
And the leading theory for that is messy.
Very messy. It's called the giant impact hypothesis. The idea is that the very young Earth collided with another protoplanet.
Not just any protoplanet, right? Something big.
Something really big, roughly the size of Mars, which is about 10% of Earth's current mass. This hypothetical impactor even has a name. Theia.
Theia.
Okay.
And it wasn't a head-on collision.
No, the models suggest it was more of a glancing blow, an oblique impact, but incredibly violent.
I can only imagine what happened to Theia and Earth.
The energy was immense. It would have melted large parts of both bodies. The iron-rich core of Theia is thought to have sunk down and merged with Earth's already forming core.
Oh.
But the impact also blasted a huge amount of vaporized rock and material, mostly from the outer layers, the mantles of both Earth and Theia, out into orbit around Earth.
And that debris cloud eventually became the moon.
Exactly. It coalesced relatively quickly, maybe within centuries or millennia, forming the moon we see today.
And the evidence for this massive collision, It's in the moon rocks, right?
It is. The composition is the key. The moon rocks brought back by the Apollo missions show that the moon is very similar in composition to Earth's mantle and crust.
But not its core.
Right. The moon has a very small iron core compared to Earth, and it's depleted in volatile elements, things that vaporize easily, like water or potassium.
Which makes sense if it formed from the outer, lighter, already heated material thrown off by the impact, while the heavier iron cores merged.
Precisely. The giant impact hypothesis elegantly explains these chemical signatures. It's why it's the leading theory.
Okay, so we have a young, molten Earth, recently smacked by a Mars-sized object, and a newly formed moon orbiting it. What about the basics for life? Atmosphere, oceans, protection.
Those came next, developing over hundreds of millions of years. The early atmosphere and the first oceans formed mainly through volcanic activity.
Outgassing, they call it.
Yeah, outgassing. Gases like water vapor, carbon dioxide, nitrogen, trapped inside the molten Earth were released through volcanoes. As the planet cooled, that water vapor condensed and rained down, forming the oceans.
Did all the water come from inside the Earth?
Probably not all of it. It's thought that a significant amount of water and ice was also delivered later by impacting comets and asteroids during the late heavy bombardment period.
Right. Okay, so we have air and water starting to form. But the young sun was also pretty nasty, wasn't it? Lots of radiation, strong solar wind.
Extremely nasty. And that's where the magnetic field comes in. It was absolutely crucial. The evidence suggests it was established fairly early, maybe by around 3.5 billion years ago.
And that field is generated deep inside the Earth.
Yes, by the churning motion of the liquid iron in the outer core. It creates a geodynamo, essentially turning the Earth into a giant magnet.
And why was that 3.5 billion year milestone so important? What did the field do?
It acted like a shield. It deflects the bulk of the solar wind, that stream of charged particles constantly flowing from the sun.
Protecting the atmosphere.
Exactly. Without that magnetic shield, the solar wind would have gradually stripped away our atmosphere, molecule by molecule, especially lighter gases like hydrogen, and broken down water vapor.
Like what might have happened on Mars.
Precisely. Mars lost its global magnetic field early on, and that's likely a major reason why it lost most of its atmosphere and water and became the cold, dry planet it is today. Earth's magnetic field basically saved our air and water, allowing life to eventually get a foothold.
Okay, so the shield is up, the oceans are forming. What about solid ground? The continents. Did they form quickly too?
That's a more debated topic. The continental crust, the lighter, thicker rock that makes up the land masses, has definitely evolved over time. There are sort of two main schools of thought, or models, based on the research we looked at.
What are they?
Well, Model 1 is simpler. It suggests a relatively steady, continuous growth of continental crust over Earth's history, right up to the present. You find rocks of all different ages purporting this.
Okay, and Model 2?
Model 2 is a bit more dynamic. It proposes that there was an initial, very rapid burst of continental crust formation early on during the Archean Eon, maybe forming the bulk of the continents quickly.
And then what happened to it?
Then, according to this model, much of that early crust has been subsequently recycled back down into the mantle through plate tectonics, and new crust formed later. It suggests a more cyclical process of creation and destruction.
Is there evidence for really early crust existing?
Oh, yes. And it's incredible evidence. Tiny, incredibly durable crystals called zircons.
Zircons, I've heard of those. They're like geological time capsules.
Exactly. Scientists have found zircon grains in ancient rocks in places like Western Australia that date back as far as 4.4 billion years.
4.4 billion. That's only, what, 140 million years after Earth first formed?
Right. Almost immediately, geologically speaking. And the chemistry of these zircons tells us they formed in environments that required liquid water, relatively cool temperatures, conditions associated with felsic crust, the kind that makes up continents.
So that suggests solid ground and water existed almost from the very beginning.
It strongly suggests it. It really challenges the older picture of the first few 100 million years, the Hadean Eon, as being entirely a molten hellscape. It seems things might have cooled down and stabilized, at least in patches, much faster than we used to think.
Wow, okay. So continents started forming early, but they didn't just stay put, did they? They've been drifting around.
Constantly drifting, colliding, and breaking apart, driven by the slow convection currents in the mantle beneath them. This leads to the amazing phenomenon known as the supercontinent cycle.
Where all the land masses periodically clump together.
Yeah, into one giant continent and then eventually break apart again. We have evidence for several of these in the past. There was Rodinia, which formed over 1 billion years ago and started breaking up around 750 million years ago.
Virginia.
Okay. Then there was Pannotia, a bit more controversial, maybe existing briefly between about 600 and 540 million years ago, around the end of the Precambrian.
And the most famous one.
Pangaea, of course,
Right.
the one we all learned about in school. It dominated the late Paleozoic and early Mesozoic eras from about 335 million years ago and started breaking apart around 180 million years ago.
Giving rise to the continents we see today.
Exactly. The Atlantic Ocean started opening up then. These cycles have massive impacts on everything: sea levels, ocean currents, global climate, and of course the evolution and distribution of life.
And intertwined with these tectonic shifts are the dramatic climate swings, the ice ages.
Earth's history is punctuated by periods of intense cold and glaciation. The most recent pattern of severe ice ages really kicked into high gear during the Pleistocene epoch, starting about 2.6 to 3 million years ago.
And these aren't just random cold snaps, there's a rhythm to them.
There seems to be, yeah. Driven by subtle, predictable changes in Earth's orbit around the sun. The Milankovitch cycles we'll probably get to later. These orbital wobbles cause variations in the amount of sunlight reaching different parts of the Earth, leading to glacial cycles with rough periodicities of about 21,000, 41,000, and 100,000 years.
And the last ice age, the one people often talk about.
The peak of the last glacial period was around 20,000 years ago. But the actual end of that cold spell, the transition to our current warmer interglacial period, the Holocene, happened remarkably recently, about 11,700 years ago.
Geologically, that's like yesterday afternoon.
Pretty much. It's a reminder that the climate system we experience now is just one phase in a much longer dynamic story.
Okay, so the planet is physically taking shape. We have oceans, an atmosphere shielded by a magnetic field, continents moving around. The stage is set for life.
Indeed. And the origin of life is still one of the biggest mysteries in science, but we can trace the timeline based on the evidence we do have.
It started with chemistry, right? Simple molecules becoming more complex.
Exactly. The idea is that in the early oceans, or perhaps in hydrothermal vents, chemical reactions started producing more complex organic molecules. Eventually, some of these molecules developed the ability to make copies of themselves, self-replication.
The first precursors to RNA or DNA.
Something like that. We think these first self-replicating molecules appeared maybe around 4 billion years ago.
4 billion. Wow.
And then perhaps 500 million years later, so around 3.5 billion years ago, we see evidence suggesting the existence of the last universal common ancestor, or LUCA.
LUCA. So that's the organism from which all life currently on Earth, from bacteria to blue whales to us, eventually descended.
That's the concept, yes. The single origin point for the tree of life as we know it.
What was the next huge leap forward for this early life?
Arguably, the evolution of photosynthesis. This was a game changer.
Because it allowed life to use sunlight directly for energy.
Precisely. Instead of relying on chemical energy from rocks or vents, organisms could now tap into the most abundant energy source available, the sun. They use sunlight, water, and carbon dioxide to produce energy.
And as a byproduct?
Oxygen. Molecular oxygen, O2. Initially, this oxygen reacted with iron dissolved in the oceans, creating vast deposits of rusted iron formations we see in the rock record. But eventually, the oxygen started building up in the atmosphere itself.
Which leads to another transformative event.
Absolutely. The single most profound change life has ever wrought on the planet. The Great Oxidation Event, or GOE.
When did this happen?
The major phase was around 2.4 to 2 billion years ago. Photosynthetic cyanobacteria, sometimes called blue-green algae, had been pumping out oxygen for a long time, but this is when it really started accumulating significantly in the atmosphere.
And you called it an event. Was it catastrophic?
Well, for the existing life forms at the time, which were mostly anaerobic, meaning they didn't use oxygen and in fact found it toxic, yes, it was likely a catastrophe, a mass extinction event caused by oxygen poisoning.
But for the future of life?
It was revolutionary. The presence of abundant free oxygen in the atmosphere made possible a much more efficient form of energy metabolism, aerobic respiration, the kind we use.
Okay.
And it had another absolutely critical side effect. High up in the atmosphere, some of that O2 reacted under sunlight to form O3.
Ozone.
Ozone, yes. And the formation of the ozone layer was monumental.
Why? What did the ozone layer do?
It absorbs most of the sun's harmful high-energy ultraviolet, or UV, radiation. Before the ozone layer formed, the land surface was basically sterilized by intense UV. Life was largely confined to the oceans or perhaps beneath rocks.
So the ozone layer acted like planetary sunscreen then.
Exactly. It allowed life to finally emerge from the water and begin colonizing the land surfaces sometime after the GOE.
We can actually see traces of this incredibly ancient life in rocks, can't we?
We can. Some of the earliest compelling evidence comes from fossils of microbial mats called stromatolites. We find structures that look like fossilized mats dating back as far as 3.48 billion years. And there's even potential evidence that's older, though more debated. For instance, traces of biogenic graphite carbon that seems to have been processed by life found in rocks in Greenland dating back to 3.7 billion years ago.
It pushes life's origins back incredibly far.
It really does. Life got started relatively early in Earth's history.
Okay, so life is evolving, diversifying. But then the planet throws some major curveballs, climatically speaking. You mentioned ice ages before, but there were some extreme ones, right? The snowball Earth periods.
Ah, yes. The snowball Earth hypothesis. This refers to several periods, particularly in the late Proterozoic eon, roughly between maybe 720 and 655 million years ago, where evidence suggests the entire planet, or almost the entire planet, might have been covered in ice. Glaciers reaching the equator.
A completely frozen world. How could life even survive that?
It's a big question. Maybe in pockets of open water near volcanic vents or under the ice. But what's fascinating is what happened after these extreme cold snaps.
What happened?
Well, shortly after the last major snowball Earth events ended, around 540 million years ago, we see the beginning of something extraordinary in the fossil record. The Cambrian explosion.
The sudden appearance of complex animals.
Exactly. Suddenly, over a relatively short geological time span, maybe 10, 20 million years, we see the emergence of almost all the major animal body plans, the phyla that exist today. Hard shells, exoskeletons, segmentation, primitive eyes, an explosion of diversity and complexity.
And the theory is that the stress of the snowball Earth somehow triggered this.
That's one leading idea. Perhaps the extreme conditions wiped out earlier, simpler ecosystems opening up ecological space, or maybe the intense weathering after the ice melted flushed nutrients into the oceans, fueling evolution. The exact link is still debated, but the timing is suggestive.
But this explosion of life wasn't the end of the story. Evolution continued, but it was punctuated by setbacks, major ones.
Unfortunately, yes. Mass extinctions are a recurring theme in Earth's history. Since the Cambrian, there have been at least 5 truly catastrophic mass extinction events, where a huge percentage of global biodiversity was wiped out in a relatively short time.
The big 5, like the Permian extinction, the worst one.
Right. The end Permian extinction, about 252 million years ago, was devastating. Up to 96% of marine species and 70% of terrestrial vertebrate species might have gone extinct, likely linked to massive volcanic eruptions in Siberia.
And the most recent major one, the one everyone knows.
The Cretaceous-Paleogene, or KPG, extinction event. 66 million years ago.
The dinosaur killer.
That's the one. Marked by the impact of a large asteroid or comet in the Yucatan Peninsula region. It wiped out all the non-avian dinosaurs, the giant marine reptiles, the pterosaurs, fundamentally reshaped life on Earth.
But not everything died.
No. Crucially, smaller animals tended to survive better, including significantly early mammals. They were mostly small nocturnal creatures during the age of dinosaurs.
Oh, with the dinosaurs gone.
Exactly. The extinction opened up vast ecological niches. Mammals rapidly diversified, grew larger, and eventually came to dominate many terrestrial ecosystems, which eventually leads us to, well, us.
Our own species, Homo sapiens, were relative newcomers on the scene.
Very recent newcomers. Anatomically modern humans emerged in Africa maybe around 300,000 years ago.
And what drove our specific evolutionary path? What made us different?
It seems to be a combination of factors. Bipedalism, walking upright, freed our hands.
For tool use.
Right. Increasingly sophisticated tool use. And alongside that, the development of complex language and communication.
Which allowed for cooperation, planning, passing on knowledge.
All of that. These factors are thought to have driven a feedback loop leading to significant brain expansion and increased cognitive abilities, abstract thought, problem solving, culture.
Making us, for better or worse, the most profoundly influential biological force on the planet today.
Unquestioned.
All right, let's shift gears from the deep past to the very distant future. This part feels a bit bleak. Earth's ultimate fate seems sealed, doesn't it? And it's tied directly to the sun.
It is, unfortunately. The long-term future of Earth on billion-year timescales is entirely dictated by the evolution of our star. The sun isn't static.
It's getting hotter.
Slowly, but inexorably. As the sun fuses hydrogen into helium in its core, the core contracts and heats up, causing the outer layers to burn brighter. It's a natural part of stellar evolution for stars like ours.
How much brighter are we talking?
The models project about a 10% increase in the sun's luminosity over the next 1.1 billion years.
Okay. 10% doesn't sound that dramatic over a billion years.
But the consequences for Earth are profound. Even that gradual increase in solar radiation will start a devastating cascade long before the sun actually, engulfs the planet.
What kind of cascade? What happens first?
It triggers something called a moist greenhouse effect, and it messes with the Earth's thermostat, the carbon cycle.
How does that work?
Okay, so increased temperature speeds up evaporation, putting more water vapor, a powerful greenhouse gas, into the atmosphere. This warms things further. But critically, it also accelerates the weathering of silicate rocks on the continents.
Weathering. Like rain breaking down rocks.
Exactly. And that chemical weathering process draws carbon dioxide, CO2, out of the atmosphere and eventually locks it away in carbonate rocks like limestone on the ocean floor.
So the Earth tries to cool itself down by removing CO2.
It does. It's a natural negative feedback loop that has helped regulate Earth's climate for billions of years. But when the sun is constantly getting hotter, this feedback goes into overdrive.
It removes too much CO2. That sounds counterintuitive. Isn't less CO2 good?
Not when you go too far. Plants need CO2 for photosynthesis. It's their food. If the atmospheric concentration drops too low, plants start to die off on a massive scale.
What's the critical level?
Research suggests that when CO2 levels fall below about 10 parts per million, which is incredibly low compared to today's levels, most current forms of plant life simply can't survive.
And when might that happen?
The estimates vary, but it could be somewhere between 100 million and 900 million years from now, depending on the exact dynamics.
Okay. So no plants. What does that mean for the rest of life?
It's the end game for complex life as we know it. If plants can't photosynthesize, they stop producing oxygen. The oxygen in the atmosphere gets used up over geological time, and it's not replenished. So animal life, including any far future descendants we might have, would face extinction due to suffocation. The loss of the food base first, then the loss of breathable air.
So long before the Earth boils, it becomes unlivable because the carbon cycle fails.
That seems to be the most likely scenario for the end of complex life, yes. Driven by the sun's increasing heat indirectly.
But the direct heat does eventually become the main problem.
Oh, yes. As the sun continues to brighten, maybe around 1.5 billion years from now, the model suggests Earth's average surface temperature could reach 100 degrees Celsius.
The boiling point of water.
Exactly. The oceans begin to boil away into the atmosphere.
A runaway greenhouse effect.
A full-blown one-away greenhouse effect. All that water vapor traps even more heat. Within maybe 1.6 to 3 billion years, all the ocean water will likely have evaporated and been lost to space, broken down by solar radiation high in the atmosphere.
Leaving behind
a hot, dry, desolate world, likely hotter than Venus is today, completely sterilized.
And that's still before the sun's final act.
That's right. The really dramatic changes to the sun itself happen much later, in about 5 billion years from now.
What then?
The sun runs out of hydrogen fuel in its core. It starts fusing helium into heavier elements, which burns much hotter. This causes the sun's outer layers to expand enormously. It becomes a red giant star.
How big?
Maybe 250 times its current radius, big enough to potentially swallow Mercury and Venus.
What about Earth? Do we get swallowed too?
That's actually uncertain. It's a bit of a close call, according to the astrophysicists.
How can it be uncertain? Surely if it expands that much.
Two things happen. As the sun expands into a red giant, it also loses a significant amount of its mass through very strong solar winds. Less mass means less gravity. So the orbits of the remaining planets, including Earth, should actually drift outwards. Earth might move out to around 1.7 astronomical units, AU, further away than Mars is now.
So maybe we escape being engulfed.
Maybe. But the sun's outer atmosphere, its corona, will be vastly expanded too. Even if Earth's orbit moves out, it might still encounter the tenuous outer layers of the red giant sun.
And that would be bad.
Very bad. The drag from moving through that gas, combined with intense tidal forces from the nearby giant star, could cause Earth's orbit to decay. We might spiral inwards after all.
And then?
then we get vaporized. The rock, the metal, everything that makes up our planet would be incorporated into the sun's outer layers.
So best case scenario, we're a roasted cinder orbiting further out. Worst case, we become part of the sun.
That sums it up pretty well. Either way, it's a guaranteed scorched destiny for the planet itself, billions of years down the line.
Okay, let's pull back from that fiery future and look inside the Earth now. The mechanics that keep things running today. We started with Chimborazo and the equatorial bulge.
Right, the fact that Earth isn't a perfect sphere, but an oblate ellipsoid. It's wider at the equator than it is pole to pole by about 43 kilometers, a direct result of its rotation.
And measuring this lumpy shape is a whole field of science.
It is, yeah. It's called geodesy. Because the physical surface is so irregular, with mountains and valleys, and even the underlying gravity field isn't uniform, scientists need a reference surface.
Not just sea level.
Sea level is a good approximation, but it changes with tides and winds. So they use a theoretical concept called the geoid.
The geoid. Okay, what is that exactly?
Imagine the ocean could flow freely over the entire globe, responding only to Earth's gravity and rotation with no wind or tides, the shape that water surface would take. That's the geoid.
So it's like a map of the Earth's gravitational level.
Exactly. It's an equipotential surface. It's lumpy, following variations in mass distribution inside the Earth, but it provides the crucial zero-point reference for measuring topographic heights, like mountain elevations.
Okay, now let's go deeper. Inside the Earth, it's layered like an onion, right?
Very much so. We typically describe the layers in two ways: by their chemical composition and by their physical properties, specifically how they deform or flow their rheology.
Let's start with chemistry. Outermost layer.
That's the crust. It's the thin, solid, rocky shell we live on, made mostly of silicate rocks.
How thin?
It varies a lot. Under the oceans, the oceanic crust is relatively thin, maybe only 6 kilometers thick on average. But under the continents, the continental crust is much thicker, typically 30 to 50 kilometers, even thicker under major mountain ranges.
And below the crust?
Below the crust is the mantle. Chemically distinct, much richer in iron and magnesium than the crust. There's a short boundary between the crust and the mantle that seismologists can detect because seismic waves suddenly change speed there.
That's the moho.
That's the one. The Mohorovičić discontinuity, usually just called the moho, it marks the base of the crust.
Okay, so that's the chemical layering near the surface. What about the physical properties, the retinology?
This is where we talk about the lithosphere and the astronosphere. The lithosphere isn't just the crust. It includes the crust plus the uppermost rigid part of the mantle that's mechanically coupled to it.
So the lithosphere is the rigid outer plate.
Exactly. It's the tectonic plate. And the lithosphere floats or rides on top of the layer beneath it, which is the asthenosphere.
And the asthenosphere is softer.
Softer isn't quite the right word because it's still solid rock, but it's much hotter and under immense pressure, causing it to behave like a very, very viscous fluid over geological timescales. Think extremely thick tar or putty.
Ah, okay. So it can flow very slowly.
Right. It's less rigid, has lower viscosity than the lithosphere above it, and the slow convection currents within the asthenosphere and the deeper mantle are what drive the movement of the lithospheric plates above. That's the engine of plate tectonics.
Got it. And the mantle itself goes down pretty deep.
Oh, yeah. The mantle extends all the way down to about 2,890 kilometers below the surface. It makes up the vast majority of Earth's volume.
And beneath the mantle?
We reach the core, which, again, has layers.
Liquid and solid.
Correct. There's a liquid outer core, extending from the base of the mantle down to about 5,150 kilometers. And then right at the center is the solid inner core.
Why is the outer core liquid but the inner core solid, if the inner core is even hotter?
Pressure. The pressure at the center of the Earth is absolutely immense, millions of times atmospheric pressure. Even though the inner core is incredibly hot, that extreme pressure forces the iron-nickel alloy there into a solid state. The outer core is still super hot, but the pressure is slightly lower, allowing it to remain liquid.
And that liquid outer core is where the magnetic field comes from.
Yes, the convection currents in that churning, electrically conductive liquid iron act like a giant dynamo, generating Earth's magnetic field.
And I read something fascinating. The inner core might be skinning slightly faster than the rest of the planet.
That's what some seismic studies suggest, yeah. It seems the solid inner core might be rotating just a tiny bit faster, maybe gaining a fraction of a degree of longitude each year relative to the surface. The implications for the dynamo and heat flow are still being researched, but it's a cool idea.
Okay, putting it all together, we said Earth is the densest planet in the solar system. What's the actual number?
The mean density is about 5.513 grams per cubic centimeter. Water is 1 g/c. Typical surface rock is maybe 2.7, 3.0. So yeah, Earth is very dense overall.
And what's it mostly made of, element-wise?
By mass, the top three elements for the whole planet are iron, about 32.1%, oxygen, 30.1%, and silicon, 15.1%. Magnesium is next.
But that's skewed by the core, right? The crust is very different.
Very different. The crust is dominated by oxygen and silicon, making silicate minerals, along with aluminum, iron, calcium, sodium, potassium, magnesium, much lighter elements overall. The core, on the other hand, is believed to be overwhelmingly iron, maybe 88.8%, with about 5.8% nickel and some lighter elements like sulfur mixed in.
And all that internal heat keeping the outer core liquid. Where does it come from? Is it just left over from formation?
That's part of it, yes. Primordial heat from the accretion process and the energy released as the dense iron core formed and sank. But a huge chunk of the Earth's internal heat budget, maybe around half, comes from an ongoing source: radiogenic heat.
Radioactive decay.
Exactly. The slow radioactive decay of long-lived, unstable isotopes that are naturally present in the mantle and crust. The most important ones are potassium-40, uranium-238, uranium-235, and thorium-232. As these atoms decay over billions of years, they release energy, keeping the interior hot.
How hot does it get down there, at the center?
Estimates put the temperature at the boundary between the inner and outer core at around 5,200 degrees C, and the very center of the inner core might reach up to 6,000 degrees Celsius.
As hot as the surface of the sun.
Pretty much, yeah. That intense heat is what drives the convection in the outer core for the magnetic field and the slower convection in the mantle that drives plate tectonics.
Let's talk more about that magnetic field, generated in the outer core.
Right, by that dynamo process. And the field it generates extends far out into space, creating the magnetosphere.
Our protective bubble.
Our bubble, exactly. It acts approximately like a dipole field, like a giant bar magnet tilted slightly relative to the rotation axis, with a north and south magnetic pole.
And its main job is deflecting the solar wind.
Yes. That constant stream of charged particles from the sun would otherwise bombard the upper atmosphere, stripping it away over time and making the surface hazardous for life. The magnetosphere carves out a cavity in the solar wind, forcing most of it to flow around the Earth.
You mentioned it's not symmetrical.
Not at all. On the side facing the sun, the day side, the solar wind pressure squashes the magnetosphere inwards, typically extending out to maybe 10 Earth radii.
Okay.
But on the night side, away from the sun, the field lines are stretched out into a very long tail, the magnetotail, which can extend hundreds of Earth radii, way past the moon's orbit.
And inside this magnetosphere, there are zones where particles get trapped.
Yes, there are several regions of trapped plasma. Closest in is the plasmasphere, which is relatively cool, dense plasma sort of co-rotating with the Earth. Further out, you have the ring current carrying energetic ions. And perhaps most famously, the Van Allen radiation belts.
The Van Allen belts, what are they?
They are typically two donut-shaped regions surrounding the Earth, filled with highly energetic charged particles, electrons, and protons trapped by the magnetic field lines spiraling back and forth between the magnetic poles. They represent a significant radiation hazard for satellites and astronauts.
Wait, if the field is generated by convection in a chaotic liquid core, is it constantly moving? And I heard that the poles actually reverse sometimes. How does that instability affect us?
That's an excellent question. And yes, the field is definitely not static. The convection in the outer core is turbulent and chaotic.
So the magnetic poles wander.
They do. The magnetic North Pole, for example, has been drifting quite significantly in recent decades, moving away from Arctic Canada towards Siberia. This requires updates to navigation systems.
And the reversals, they really flip.
They really flip. The entire magnetic field polarity reverses. What was magnetic north becomes magnetic south, and vice versa. The geological record, preserved in magnetized rocks on the seafloor and in lava flows, shows this has happened many, many times throughout Earth's history.
How often?
It's irregular. The average time between reversals is maybe a few 100,000 years, but it's highly variable. The last major reversal, the Brunhes-Matuyama reversal, happened about 773,000 years ago, so we're arguably overdue for one, statistically speaking.
What happens during a reversal? Does the shield just switch off?
Not completely switch off, but it significantly weakens and becomes much more complex. Instead of a dominant dipole field, you might get multiple weaker north and south poles scattered across the globe. The whole process might take several thousand years to complete.
And a weaker shield means
Potentially more solar and cosmic radiation reaching the surface. The exact effects on life or climate are still debated and researched. It probably wouldn't be an immediate apocalypse, but it could increase mutation rates and potentially affect sensitive technologies. It's an active area of study. Okay, let's zoom out again and think about Earth's motion through space. Its orbit and rotation define our year, our day, and our seasons.
The orbit first. We're about 150 million kilometers from the sun, on average.
Right. That average distance is defined as 1 astronomical unit, or AU, and it takes us 365.2564 days to complete one full orbit around the sun relative to the background stars. That's the sidereal year.
And we're moving pretty fast to cover that distance.
We really are. Our average orbital speed is almost 30 kilometers per second.
Wow, what's that? 29.7827 kilometers, the source said.
That's the number. To put it in perspective, that's fast enough to travel a distance equal to Earth's diameter, about 12,742 kilometers in less than 8 minutes.
Incredible. Okay, so that's the year. What about the day? Our rotation.
Our rotation gives us the cycle of day and night. But there are actually two slightly different ways to measure a day.
Oh.
There's the mean solar day. That's the average time it takes for the sun to appear in the same position in the sky, say, from one noon to the next. By definition, we divide this into 24 hours, or 86,400 seconds.
Okay, that's the day we live by. What's the other one?
The sidereal rotation period. This is the time it takes for Earth to rotate exactly 360 degrees relative to the distant fixed stars. Because Earth is also moving along its orbit during that rotation, this period is slightly shorter than the solar day.
How much shorter?
It's 23 hours, 56 minutes, and 4.100 seconds. About 4 minutes shorter.
Huh. And you mentioned earlier the day is actually getting slightly longer over time.
It is, yeah. Very, very slowly. The mean solar day is currently lengthening by maybe 0 to 2 milliseconds compared to that standard 86,400 second definition. It's mainly due to tidal deceleration. The gravitational pull of the moon raises tides on Earth, both in the oceans and the solid body itself. These tidal bulges get dragged slightly ahead or behind the Earth-Moon line by Earth's rotation.
Creating friction.
Essentially, yes. The moon's gravity pulls back on these bulges, creating a torque that constantly slows down Earth's rotation, like applying brakes. It's a tiny effect day to day, but it adds up over millions of years. Days used to be much shorter in the distant past.
Okay, so we have orbit giving the year, rotation giving the day. What gives us seasons?
That's the axial tilt. Earth's rotation axis isn't perfectly upright relative to its orbital plane around the sun. It's tilted.
By how much?
The current tilt, or obliquity, is about 23.439 degrees.
And because of that tilt, different parts of the Earth get more direct sunlight at different times of the year.
Exactly. When the northern hemisphere is tilted towards the sun, it receives more direct sunlight, longer days, and experiences summer. At the same time, the southern hemisphere is tilted away, gets less direct sunlight, shorter days, and experiences winter. 6 months later, it reverses.
And the points where the tilt is maximal or minimal define key moments.
Right. The solstices are when one hemisphere is tilted most directly towards the sun, summer solstice, or most directly away, winter solstice. The equinoxes occur when the tilt is sideways relative to the sun, so the sun shines directly on the equator, and day and night are roughly equal everywhere. These astronomically define the start of the seasons.
Now, you mentioned before that these orbital factors, the tilt, the shape of the orbit, they aren't perfectly stable either. They wobble over long timescales.
That's right. They change in predictable, cyclical ways known as the Milankovitch cycles, named after the Serbian scientist Milutin Milankovic, who calculated them.
And these cycles are linked to the ice ages.
They are considered the primary pacemaker for the major glacial-interglacial cycles of the past few million years. Yeah. There are three main components to these cycles.
What are they?
First, there's eccentricity. That's the shape of Earth's orbit. It varies from being nearly circular to slightly more elliptical or stretched out. This cycle takes about 100,000 years and also has a longer 400,000-year component.
Okay, orbit shape. What else?
Second is obliquity, which is the axial tilt itself. It doesn't stay fixed at 23.4 degrees. It nods up and down slightly, varying between about 22.1 and 24.5 degrees over a cycle of about 41,000 years. More tilt means more extreme seasons.
And the third one?
Third is precession. This is the wobble of the Earth's axis, like a spinning top slowing down. It changes the timing of the seasons relative to Earth's position in its orbit, specifically relative to perihelion, the point closest to the sun. This cycle takes about 26,000 years.
So it's the combination of these three overlapping cycles, eccentricity, obliquity, precession, that changes the pattern of sunlight hitting the Earth.
Precisely. They alter the amount and distribution of solar radiation or insolation received by the Earth, particularly at high latitudes where ice sheets form. When the cycles align in a way that favors cooler summers in the northern hemisphere, snow doesn't melt, ice sheets can grow, and you can trigger an ice age. When they align differently, you get warmer periods like the one we're in now.
It's amazing that these subtle astronomical cycles can have such profound effects on the entire planet's climate.
It really highlights the interconnectedness of the Earth system.
Okay, let's turn our attention to Earth's companion, the Moon. It's unusually large for a moon, isn't it, compared to Earth?
It really is. Relative to its parent planet, the Moon is the largest satellite in the solar system. Its diameter is about 1/4 of Earth's diameter. That's huge compared to, say, Mars's tiny moons, or even the moons of Jupiter and Saturn relative to their giants.
And its gravity has noticeable effects here. Tides, obviously.
Tides are the most obvious effect, yes. The Moon's gravitational pull creates bulges in Earth's oceans, leading to the daily rise and fall of sea levels. The Sun also contributes to tides, but the Moon's effect is stronger because it's so much closer.
And that tidal interaction is also what's slowing Earth's rotation down.
Correct. That's the tidal deceleration we talked about. The energy lost by Earth's slowing rotation gets transferred to the Moon's orbit.
Meaning the Moon is actually moving away from us.
Yes, very slowly. Laser measurements show the Moon is currently receding from Earth at a rate of about 3.8 centimeters per year. About the speed your fingernails grow.
Wow. And another effect of these strong tides is that the Moon is tidally locked, right?
Yes. Tidal locking means the Moon rotates on its axis in exactly the same amount of time it takes to orbit the Earth. The result is that it always keeps the same face pointed towards us. We never see the far side of the Moon directly from Earth.
Now here's something truly amazing. The cosmic coincidence that gives us perfect solar eclipses.
Ah, yes. The grand coincidence. It's really quite remarkable geometry.
Explain it.
The Sun's diameter is about 400 times larger than the Moon's diameter. But, by complete coincidence, the Sun is also currently about 400 times farther away from Earth than the Moon is.
So the size difference and the distance difference cancel each other out almost perfectly.
Exactly. From our perspective here on Earth, the Sun and the Moon appear to be almost exactly the same size in the sky, about half a degree across.
Which means the Moon can sometimes perfectly cover the Sun's disk.
Precisely. This allows for total solar eclipses, where the Moon completely blocks the Sun's bright face, revealing the faint outer atmosphere, the corona. It also allows for annular eclipses, where the Moon is slightly farther away in its elliptical orbit, so it appears slightly smaller and leaves a ring of fire visible around its edge. This near-perfect match in apparent size is unique to the Earth-Moon system in our solar system.
It's just incredible luck. But the Moon's importance goes way beyond providing spectacular eclipses, doesn't it? It's crucial for Earth's stability.
Absolutely vital. Many scientists argue that the presence of our large moon has played a key role in making Earth habitable over the long term, primarily by stabilizing our axial tilt.
How does it do that?
The moon's gravitational pull acts like an anchor, damping down the chaotic fluctuations in Earth's obliquity, the tilt, that would otherwise occur due to gravitational tugs from other planets, especially Jupiter.
So without the Moon, our tilt would wobble wildly.
Simulations suggest yes. Without the Moon, Earth's tilt could potentially swing chaotically between maybe 0 degrees and perhaps as much as 85 degrees over millions of years.
That would cause extreme climate swings, from no seasons to seasons where the poles point almost directly at the sun.
Exactly. It would make it incredibly difficult for stable climates to persist, and likely much harder for complex life to evolve and survive. Mars, which lacks a large moon, is thought to undergo these kinds of large, chaotic tilt variations.
So the Moon acts as a climate stabilizer for Earth.
That's the idea. By keeping our axial tilt relatively stable around its current 23.4 degrees, the Moon has helped ensure more moderate, predictable climate zones over geological time, which was likely a critical factor in the development and persistence of life. Okay, so we have the solid Earth, the Moon stabilizing it. Let's talk about the fluids that make life possible. Water and air. The hydrosphere first. The oceans are just immense.
How much water are we talking about? Total volume or mass?
The total mass of the oceans is estimated at about 1.35 times 10 to the power of 18 metric tons. That's 1.35 billion tons.
Wow. But compared to the whole Earth's mass.
It's actually a tiny fraction, only about 444 hundredth of Earth's total mass. So while the oceans cover the surface, they are just a very thin layer compared to the planet's bulk.
And we said earlier, most of this water isn't fresh water.
Not at all. About 97.5% of all the water on Earth is saline, salty ocean water. Only 2.5% is fresh water.
And where is that crucial 2.5% fresh water found?
The vast majority of it, about 68.7%, is locked up as ice in glaciers and ice caps, mostly in Antarctica and Greenland.
Okay, so not easily accessible.
Not at all. Another 30% or so is groundwater, hidden beneath the surface. Only a very small fraction, less than 1.3% of the world's fresh water, is surface water in lakes, rivers, swamps, and the atmosphere.
Makes you realize how precious, easily accessible fresh water really is.
Absolutely.
Yeah.
And the oceans themselves, that 97.5%, have a fairly consistent saltiness or salinity.
What's the average?
Around 35 grams of dissolved salts per kilogram of seawater, mostly sodium chloride, common table salt, but lots of other dissolved ions too.
And these massive bodies of water, they do more than just hold water, right? They drive climate.
Hugely important for climate regulation. Oceans act as enormous heat reservoirs. They absorb vast amounts of solar energy, especially near the equator, and transport that heat towards the poles through ocean currents.
Helping to moderate global temperatures.
Exactly. Without ocean currents distributing heat, the equator would be much hotter and the poles much colder. They also drive major weather patterns, things like the El Niño Southern Oscillation or ENSO.
El Niño and La Niña.
Right. That's a periodic fluctuation in sea surface temperatures and atmospheric pressure across the tropical Pacific Ocean, but it has ripple effects on weather patterns across the globe, droughts in some places, floods in others. It's a key example of ocean-atmosphere interaction.
And there are deeper currents, too. The global conveyor belt.
Yes, the thermohaline circulation. This is a massive, slow-moving system of deep ocean currents driven by differences in water density, which depends on both temperature, thermo, and salinity. Cold, salty water is denser and sinks near the poles, flowing along the ocean floor towards the equator, while warmer surface waters flow towards the poles to replace it.
And this belt distributes heat globally over long time scales.
Yes, it plays a critical role in long-term climate stability and nutrient distribution in the oceans. It takes hundreds, maybe thousands of years for water to complete the circuit.
Okay, so that's the water. Now for the air. The atmosphere. What's it made of, mostly?
If you take a sample of dry air, ignoring water vapor for a moment, it's overwhelmingly nitrogen, about 78.084%.
Nitrogen. Not oxygen.
Nope, nitrogen is the bulk gas. Oxygen, which is crucial for us to breathe, is second, at about 20.946%.
So together, that's 99%. What's the last 1%?
Most of the remainder is argon, an inert gas, at about 0.934%. Then you have trace amounts of other gases, including carbon dioxide, neon, helium, methane, krypton.
And carbon dioxide is in that tiny trace amount, even though we talk about it so much.
Yes. Currently, CO2 makes up only about 0.04% of the atmosphere, roughly 420 parts per million. But despite its small concentration, it plays a huge role because it's a greenhouse gas.
Along with water vapor.
Exactly. Water vapor is the most variable component of the atmosphere, ranging from maybe 0.01% in very cold, dry air up to 4% in hot, humid air. On average, it's around 1%. And it's the most important greenhouse gas on Earth.
Which brings us back to the greenhouse effect. We often hear about it negatively now, but you stressed before it's essential for life.
Absolutely essential. Here's how it works. The sun warms the Earth's surface. The warm surface then radiates heat back outwards, mostly as infrared radiation. Greenhouse gases in the atmosphere, primarily water vapor and CO2, but also methane, nitrous oxide, and others are good at absorbing this outgoing infrared radiation. They trap some of that heat, preventing it from immediately escaping back into space.
Like a blanket.
Like a planetary blanket, exactly. And this trapped heat warms the lower atmosphere and the surface.
And without this natural greenhouse effect,
Earth would be incredibly cold. Calculations show that without it, the global average surface temperature would be around minus 18 degrees Celsius, well below the freezing point of water.
wow, everything would be frozen.
Pretty much. The natural greenhouse effect raises the average temperature by about 33 degrees Celsius, bringing it up to the current, much more comfortable global average of around 15 degrees Celsius.
Making liquid water possible on the surface.
Which is the key to life as we know it. So the natural greenhouse effect isn't the problem. The problem is the enhancement of that effect by human activities adding extra greenhouse gases.
Got it. Now, just like the oceans have currents, the atmosphere is constantly moving too. What drives that?
Same fundamental reason. uneven heating by the sun. The equator receives much more intense solar energy than the poles. This temperature difference creates pressure differences, and air flows from high pressure to low pressure, trying to even things out,
Creating winds.
creating global wind patterns. Warm air rises at the equator, flows towards the poles high up, cools and sinks in the subtropics, and flows back towards the equator near the surface. Earth's rotation complicates this, deflecting the winds, the Coriolis effect, creating large circulation cells and dominant wind belts.
Like the trade winds near the equator.
Exactly. The trade winds blowing towards the equator and the westerlies blowing from west to east in the mid-latitudes. These large-scale patterns steer weather systems around the globe.
And based on these temperature and precipitation patterns, we classify different regions into climate zones.
Yes, climatologists use various classification systems. One of the most widely used is the Köppen climate classification. It divides the world into 5 main climate groups, based primarily on temperature and precipitation patterns. A, tropical, B, arid, C, temperate, D, continental, and E, polar, with further subdivisions based on seasonal variations. It gives a good, broad overview of global climate diversity.
Okay, one last thing on the atmosphere, the layers going upwards. We live in the troposphere.
Right, the troposphere is the lowest layer where all the weather happens, extending up maybe 8 to 15 kilometers. Above that is the stratosphere.
That's where the ozone layer is.
Yes, the ozone layer, which absorbs UV radiation, is primarily located in the stratosphere up to about 50 kilometers. Temperatures actually increase with height in the stratosphere because of that UV absorption.
Yeah.
Above the stratosphere is the mesosphere, up to about 85 kilometers. Temperatures decrease again here, reaching the coldest temperatures in the atmosphere. Most meteors burn up in this layer.
And above that?
The thermosphere. Here, temperatures start to rise dramatically again with altitude because the thin air absorbs high-energy solar radiation. This layer hosts the auroras and many satellites, including the International Space Station. Beyond that is the exosphere, which gradually fades into space.
Is there a defined edge to the atmosphere, where space begins?
It's a gradual transition, but the commonly accepted boundary for aeronautical and space purposes is the Kármán line, typically defined at an altitude of 100 kilometers, about 62 miles, above sea level. Above that, the air is considered too thin to support aerodynamic flight.
Okay, we've covered the planet's formation, its interior, its movements, its water and air. Now we arrive at the most recent major influence on Earth. Humanity.
A very recent influence in geological terms, but an incredibly powerful one. As we said, anatomically modern humans emerged in Africa around 300,000 years ago.
We didn't stay there. We spread out across the globe.
We did, migrating out of Africa and eventually colonizing almost every habitable landmass on the planet. This global expansion really accelerated after the development of agriculture.
When did agriculture begin?
It seems to have started independently in several regions, but generally around 12,000 to 10,000 years ago in the early Holocene epoch, after the last ice age ended. The 10th millennium BC is often cited. It allowed for settled societies, population growth, and eventually cities and civilizations.
And we kept exploring. Which was the last continent to be settled, or at least explored?
Antarctica. While its existence was speculated about for centuries, it wasn't definitively cited until the early 19th century, and significant exploration and the establishment of research bases only really happened in the 20th century. It remains the only continent without a permanent indigenous population.
And our global population today is huge.
It is. We're currently just over 8 billion people.
8 billion. And still growing.
Still growing, but the rate of growth is slowing down. Projections suggest the global population might peak somewhere around 10 billion, maybe in the second half of the 21st century, before potentially starting a slow decline.
Is the population distributed evenly across the land?
Not at all. There's a strong bias towards the northern hemisphere. About 90% of the world's population lives north of the equator.
Why is that?
Simply because most of the landmass is there. About 68% of Earth's total land area is in the northern hemisphere. So more land, more people. Population density varies hugely too, of course, with concentrations in fertile river valleys, coastal areas, and urban centers.
And this massive population needs resources, which puts a strain on the planet.
A tremendous strain. We rely heavily on non-renewable resources. Chief among them are fossil fuels, coal, petroleum, oil, and natural gas, which provide the bulk of our energy but formed over millions of years and are being consumed rapidly.
And minerals, too.
Yes, mineral ore bodies for metals like iron, copper, aluminum, and materials needed for construction and industry. These are also finite and often extracted through mining, which can have significant environmental impacts, habitat destruction, water pollution, energy consumption.
Our use of the land itself has been transformative.
Absolutely. Think about agriculture. Only about 10.7% of the Earth's total land surface is considered arable, meaning suitable for growing crops. That's a surprisingly small fraction.
But we use much more land than that for other things.
We do. The data shows that humans use an astonishing 33.5 million square kilometers. That's roughly a quarter of the entire ice-free land surface just for grazing livestock.
Yeah.
This extensive land use for agriculture, forestry, urbanization, and infrastructure has fundamentally altered landscapes, reduced biodiversity, and changed natural cycles.
And then there's the impact from burning all those fossil fuels.
Okay.
Climate change.
Yes. The scientific consensus is overwhelming. The burning of fossil fuels, along with deforestation and other industrial processes, has released enormous amounts of greenhouse gases, primarily CO2, into the atmosphere at an unprecedented rate.
Trapping more heat.
Exactly.
Right.
Enhancing the natural greenhouse effect and causing the planet to warm. The data is clear. By 2020, global average temperatures were estimated to be about 1.2 degrees Celsius warmer than they were in the pre-industrial era, roughly the late 19th century.
1.2 degrees. That might not sound like much to the average person, but on a planetary scale.
On a planetary scale, it's a huge amount of extra energy in the climate system. It's driving changes we're already seeing: rising sea levels, more frequent and intense heat waves, changes in precipitation patterns, melting glaciers and ice sheets, ocean acidification.
Which brings us to a really critical concept for understanding our overall impact: the idea of planetary boundaries.
Yes, this is a framework developed by scientists over the last decade or so to try and quantify the safe operating space for humanity within the Earth's natural systems.
How does it work?
They identified 9 critical Earth system processes that regulate the stability and resilience of the planet. Things like climate change, biodiversity loss, the nitrogen and phosphorus cycles, ozone depletion, ocean acidification, freshwater use, land system change, atmospheric aerosol loading, and chemical pollution, or novel entities.
9 key systems, and for each one they tried to define a boundary, a safe limit.
Exactly. A threshold beyond which there's a significant risk of triggering abrupt or irreversible environmental changes at continental or even planetary scales, changes that could seriously undermine human well-being.
So how are we doing? Are we staying within these safe boundaries?
According to the most recent assessments, no. The analysis confirms that humanity has already crossed the proposed safe boundary for 5 out of the 9 identified processes.
5 out of 9. Which ones?
The boundaries assessed as being crossed are climate change, based on CO2 concentration, biosphere integrity, which includes both the rate of species extinction and the integrity of ecosystems, land system change, the conversion of natural habitats, disruptions to the biogeochemical cycles of nitrogen and phosphorus, mainly due to fertilizer use, and the introduction of novel entities, which includes chemical pollution, plastics, etc., though this one is harder to quantify globally.
Wow, that's sobering.
What
Does it mean that we've crossed these boundaries?
It means we are fundamentally altering the planet's operating system in ways that are pushing us outside the stable environmental conditions that have prevailed during the Holocene, the period in which human civilization developed. We're increasing the risk of large-scale, potentially irreversible shifts that could destabilize societies and threaten livelihoods globally. It indicates that our current collective impact is unsustainable.
But the research also suggests it's possible to live within these boundaries.
Yes. Importantly, the experts involved generally believe it is technically possible to meet the basic needs of everyone on the planet: food, water, energy, shelter, while staying within these safe planetary limits. It requires major transformations in how we produce energy, grow food, manage land and water, and design our economies, but it's considered achievable. The challenge is political, social, and economic will.
Our understanding of our place on this planet has certainly evolved over time. Culturally, we've gone through some major shifts.
Huge shifts. For millennia, many cultures believed in a flat Earth. The idea of a spherical Earth emerged gradually, often attributed to ancient Greek philosophers like Pythagoras or Parmenides around the 6th or 5th century BC, based on observations of ships disappearing over the horizon, the shape of Earth's shadow on the moon during eclipses, and how constellations change as you travel north or south.
And then even bigger shift, realizing we weren't the center of everything.
Right. The shift from geocentrism, the Ptolemaic view that the sun, moon, planets, and stars all revolved around a fixed Earth, to heliocentrism, the Copernican view that Earth is just one of several planets orbiting the sun. That took centuries to be fully accepted, facing resistance. But it fundamentally changed our cosmic perspective. We went from being the center stage to being, well, just another player.
Our understanding of Earth's age also changed dramatically.
Oh, massively. For a long time, based on religious texts or philosophical reasoning, Earth was thought to be relatively young, maybe only thousands of years old. In the 19th century, geologists studying rock layers and fossils realized the processes they saw must have taken millions, perhaps hundreds of millions of years.
But they couldn't put a firm number on it.
Not precisely. It wasn't until the discovery of radioactivity in the late 19th century and the development of radiometric dating techniques in the early 20th century that scientists could finally measure the absolute age of rocks. That's how the age of Earth was eventually determined to be billions of years old, the current estimate of 4.54 billion years.
And perhaps the most recent profound shift in perspective came from actually seeing the Earth from the outside.
Yes, the overview effect. This term describes the cognitive shift reported by many astronauts when they see Earth from space.
What do they describe?
Seeing the Earth as a whole system, a beautiful, vibrant blue marble floating in the vast darkness of space. Seeing the thinness of the atmosphere, the lack of obvious political borders, the interconnectedness of everything.
The pictures sent back by the Apollo missions in the late 1960s and early 70s must have been revolutionary. Earthrise, the blue marble.
They were incredibly powerful. Those images are credited with having a profound impact on global consciousness. They fostered a sense of planetary unity, highlighted Earth's beauty and fragility, and are often seen as a major catalyst for the modern environmental movement. Seeing our home from the outside changed how we thought about it.
So this deep dive has taken us across an immense span of time and scale, from Earth's violent birth and the formation of the moon.
Through the slow dance of continents, the evolution of the deep interior driving magnetism and tectonics.
The emergence and incredible diversification of life, shaped by planetary events like oxidation and mass extinctions.
To the intricate workings of our oceans and atmosphere, the systems that sustain us.
And finally, to our own species' recent, powerful, and frankly dangerous impact on this delicate balance.
We've looked at Earth as a physical object governed by gravity and solar physics, and as a complex, evolving biosphere.
For our final provocative thought today, let's return to an idea you mentioned earlier, that concept of synthesis, the Gaia hypothesis.
Right. Developed initially by the scientist James Lovelock, later collaborating with biologist Lynn Margulis, starting in the 1960s and 70s.
What's the core idea of Gaia? It's not just Mother Earth personification, is it?
No, it's presented as a scientific hypothesis, though it remains somewhat controversial or debated in its stronger forms. The core concept is that Earth's living organisms, the biota, and their non-living physical environment, atmosphere, oceans, rocks, are tightly coupled and function together as a single, complex, self-regulating system.
Self-regulating how?
The idea is that life itself actively maintains and adjusts the conditions on the planet to keep them suitable for life. Things like the temperature range, the chemical composition of the atmosphere, like oxygen levels, the salinity of the oceans. Gaia theory proposes that these aren't just lucky coincidences, but are actively regulated by the totality of life interacting with the physical environment over geological time, leading to long-term habitability.
Like, the planet itself is a kind of superorganism, working to keep itself stable.
That's the analogy often used, yes.
Yeah.
A single, integrated system that maintains homeostasis, a stable internal environment, much like a living organism does.
Okay, so here's the final question for you, the listener, tying this all together.
If we entertain this Gaian perspective, that Earth functions as a coherent, self-regulating entity.
And we've just discussed the planetary boundaries framework, which shows that human activities have pushed at least 5 of this system's critical regulating processes into a danger zone.
What does that imply about our role? Are we, as intelligent life, becoming a disruptive force, a kind of planetary illness threatening the stability of the Gaian system?
Or could we potentially become the conscious, regulating part of that system, the part capable of understanding the risks and deliberately acting to restore balance and ensure long-term health?
It reframes our relationship with the planet. It's not just a resource base we inhabit. It might be an integrated system of which we are a powerful and currently destabilizing component.
So the final question for you is, if this perspective holds any truth, what responsibility does this knowledge place upon us? What actions does it demand, individually and collectively, to help maintain the stability and health of this unique living planet?